in this lesson, we're going to learn about how to evaluate the trigonometric functions that we've learned at different angle measures other than just the quadrantal angles. And I'm talking about evaluating them exactly, meaning that we end up with either a fraction as an answer or something in the form of a square root as an answer. Certainly, we have seen how to use the calculator, which can give us approximations at any angle measure, but we're going to look at some specific ones that are useful in trigonometry. To do that, we have to talk about 30, 60, 90 triangles to begin with. And 30, 60, 90 triangles, they are important, but we need to start with an equilateral triangle before we get there. So an equilateral triangle is a triangle where all angle measures are the same. And if all angle measures are the same, then those angle measures have to be 60 degrees. The reason that they have to be 60 degrees is because the total sum of all angles in a triangle is always 180 degrees. So if you have three angles that are the same, 180 divided by 3 is 60. It's also true that the side lengths opposite two angle measures that are the same are going to be equal as well. So in an equilateral triangle, all three sides are going to be the same length. I'm going to choose a length to work with, and I'm going to choose a length of 2, and it'll make sense in a moment why I'm choosing 2 rather than 1. And the reason is I want to divide this triangle into two parts. So if I draw a dashed line, for instance, and just divide it into two pieces, then I would have 90-degree angles here. The length of the base of each of the new triangles is going to be 1. So that's the reason why I chose the side length to be 2, so that when I divided it in half, I wouldn't end up with a fraction. And this angle measure here at the top is going to be 30 degrees each, because it's 60 degrees total, and I divided it in half. So each angle measure should be 30 degrees. Let me translate this into something, onto a different triangle. All right, so I'm going to write this in. We had the right angle here. This was our 60-degree angle and our 30-degree angle. Okay? And that's just when I start doing some work with the trig functions, it'll be a little bit more organized. But we're not quite done with this setup here yet. It's going to be useful to know the height of the triangle. The height of the triangle I'll label as x. How can we figure out what x is? Well, if we know two sides of a right triangle, we can always use the Pythagorean theorem to figure out the third side. And it only works in right triangles. So what happens is the sum of the squares of the two shorter sides is equal to the square of the longer side, the hypotenuse. So 1 plus x squared equals 4, or x squared equals 3. So x is the plus or minus square root of 3. In this particular case, we can just choose the positive square root, simply because in trigonometry, you choose the positive or negative depending on the quadrant that you're lying in. Since we're not really lying in a quadrant here, we're just going to use a positive length. So, coming down here, I'm going to put my lengths of sides on. So across from my 30-degree angle in the figure, so here's my 30-degree angle, the side opposite it was length 1. So this length I'll write as 1. The side opposite my 60-degree angle is this length here, root 3. So I'm going to write this in as the square root of 3. And then the side opposite my 90-degree angle is length 2. So this length is 2. Oh. There we go. Okay, so this is really important setup. So basically, in a 30, 60, 90-degree triangle, what you need to know, you have to make sure you understand and know this fact. The ratio of sides is 1 square root of 3 and 2. So when I say the ratio of sides, it means if the side opposite my 30-degree angle is 5 units long, then the side opposite my 90-degree angle has to be twice that. It has to be double. So that would be a length 10. And then the side opposite the 60-degree angle would be 5 root 3 in that case. So this is a ratio of sides. But the basic ratio is 1 square root of 3, 2. Just remember, the 1 is opposite your 30-degree angle, the square root of 3 is opposite your 60-degree angle, and then 2 is opposite your 90-degree angle. And if you get out the calculator, it might help to make a little bit more sense of that if you approximate the value of the square root of 3. So it's like 1.73. So what that means is the shortest side is opposite your smallest angle. The middle side is opposite your middle angle, and the largest side is opposite your largest angle. That's just a property of triangles. That's how things always work. So let's move from there. Now, knowing that and using SOHCAHTOA, let's evaluate some trig functions. So let's evaluate the sine of 30 degrees. So sine 30 degrees is something that we could type into the calculator to get an approximation, but let's try it on this triangle. So from this triangle, sine we know to be the ratio of the opposite side to the hypotenuse. So the side opposite 30 degrees is 1, and the side that is my hypotenuse is 2. If I use the calculator, and of course make sure you're in degree mode, you always want to keep checking that as you're working through. If I do the sine of 30 degrees, the calculator agrees with me, 0.5, which is 1/2. Okay, let's try the sine of 60 degrees. So the sine of 60 degrees, so the side opposite the 60-degree angle measure is the square root of 3. And then the hypotenuse is still 2. So let's see what the calculator thinks about that. So if I do sine 60 degrees, I get 0.8660, and it goes on for a while. But let's see what happens if I calculate the square root of 3 divided by 2. I come up with the exact same number. So this is working out as expected here. Now, one thing to note is you can't use a triangle setup like this to do sine of 90 degrees. The problem is the opposite side and the hypotenuse are both the same length. So you would always get an angle, you would always get a result of 1. It just doesn't work that way. You can't use the 90-degree angle as your observed angle in this setup. If you want to find the sine of 90 degrees, you have to do something like we did last lesson, where you will find a point on the terminal side of a quadrantal angle at 90 degrees, and then use y divided by r in order to calculate that. So any quadrantal angles, that's what you have to do. But 30 and 60, this will work for any of our trig functions. So let's say I want to do cosine 30 degrees and possibly tangent of 60 degrees, and then we'll do one of the others. So we'll do cosecant of 30 degrees. So the cosine of 30 degrees, cosine is adjacent over hypotenuse. So adjacent to the 30-degree angle is square root of 3, and then the hypotenuse is 2. Tangent of 60, that is opposite over adjacent. So this would be square root of 3 divided by 1, or just the square root of 3. Cosecant of 30, that's going to be the inverse of sine 30, which would be 2 over 1, which is 2. So that's how you would find any of the trig functions evaluated at either 30 or 60 degrees. Now let's look at how we would do this with 45-degree angle measures. So here's a 45, 45, 90 triangle. The 90-degree angle is, of course, the right angle. And then these remaining two angle measures are equal at 45 degrees. Using this setup, if I call the length of the side opposite the 45-degree angle measures 1, which according to what we said earlier would have to be the same for each one, then we can calculate what the value of r is, the length of the hypotenuse. So we can calculate it as, say, r squared equals 1 squared plus 1 squared, or r equals the square root of 2. So this length along the hypotenuse is the square root of 2. So what that means is in a 45, 45, 90 triangle, the ratio of sides is 1, 1, square root of 2. And that's important to remember so that, if you ever get stuck trying to figure out an exact value for sine or cosine or any of your trig functions at 45, 30, or 60, you can use these right triangles to come up with these as long as you know those ratio of sides, or at least how to come up with them. So for instance, let's just calculate, I want to do sine first. Sine of 45 degrees, cosine of 45 degrees, and tangent of 45 degrees. So sine of 45 degrees, you'd use either angle measure, of course, but it's the opposite side over the hypotenuse. So the opposite side is 1 over the hypotenuse of the square root of 2, which you would need to multiply by square root of 2 over itself in order to rationalize that denominator and get the square root of 2 over 2. Cosine 45 degrees, pick either angle and find the adjacent side, put that over the hypotenuse. You get the same result. So sine and cosine are the exact same value at 45 degrees. Tangent of 45 degrees is opposite over adjacent. It ends up just being 1. Reference angles. Every non-quadrantal angle in standard position has an angle whose measure is between 0 and 90 degrees that is formed by dropping a vertical line from the terminal side of the angle to the x-axis. This angle is called a reference angle. Reference angles are important because the values of the 6 trig functions are always the same as the actual angle, but may differ in sign. So what you need to understand about that is it means in order to increase the number of values that we can calculate the 6 trig functions at, we can use reference angles, knowing how to calculate them at 45, 30, and 60, and then just duplicate our results into quadrants 2, 3, and 4 simply by using reference angles. So it's a matter of making our work a whole lot simpler based off of reference angles. So they're a good thing. But let's first find a reference angle for some different angles. So starting with 125 degrees. So 125 degrees, that's going to be in quadrant 2. So I'm just going to put an angle measure in quadrant 2 and call this angle 125 degrees. Now, you take the terminal side and just put a point on it. It doesn't matter where that point is. And drop a triangle to the x-axis. And it's important. The thing about reference angles is it's always dropped to the x-axis. I often will find students that want to drop it to the y-axis instead. That's not the case with reference angles. You always use the x-axis. So that's kind of the one constant thing. So the reference angle is this angle right here that I'm going to draw in green. To figure out the measure of that, just know that, this is 180 degrees this way. So if I take 180 degrees minus 125 degrees, feel free to get your calculator out, but that should be 55 degrees. This is a 55 degree reference angle. So what's going to happen here is, and I'll just show you on the calculator, if I calculate the value of, let's say, sine at 125 degrees and the value of sine at 55 degrees, I'm going to get the exact same number. The same will be true of cosine and tangent as well, and the remaining trig functions, since they're just simply the inverses of these numbers. The only thing that might differ between these values is the sign. So the actual positive or negative sign is what I'm referring to. So what that means is you can just use the angles between 0 and 90 degrees and use a reference angle in the remaining quadrants, which reduces the amount of memorization or work that you have to do. So it's a really big help. And you would know what the sign, like the positive and negative sign, would be for each of the trig functions just using the mnemonic all students take calculus. So for instance, with all students take calculus, I would know that in quadrant 2, sine and cosecant would be positive, cosine would be negative. So if I did the cosine of 55 degrees, and then just knew in quadrant 2 it would be negative, then that means the cosine of 125 would be negative. So it's going to reduce the amount of work that we have to do. All right, theta equals 308 degrees. Well, that's in quadrant 4. So I'm just going to draw a random angle in quadrant 4. It doesn't really matter where. And I'm going to put a point on its terminal side. And what I need to do is for 308 degrees is come up with a way of determining what this angle measure is right here. That's my reference angle. So it's a triangle that's dropped to the x-axis. And figuring out what your reference angle is, there's no single formula that works here. You have to do basically a different formula for each quadrant. For quadrant 2, you take 180 minus your angle measure. Quadrant 4, you take 360 minus your angle measure. So if I take 360 minus 308, that gives me a reference angle of 52 degrees. So that reference angle, if I calculate sine of 308 and sine of 52, I'll get the same numeric value, but they might be different in positive versus negative. Okay? 67 degrees. The nice thing about quadrant 1 is that the reference angle and the angle itself are the same. So you don't have to do any transformations for quadrant 1. Everything's very straightforward there. So that's nice. 210 degrees, that puts me in quadrant 3. So just drop a triangle to the x-axis. So the 210 degree angle measure would look like this. But what I have to figure out then for quadrant 3 is what that angle is right there. So if you'll notice, it's just a little bit beyond 180 degrees. So to figure out what that angle is, I need to do 210 minus 180 to kind of figure out what portion of this angle is beyond 180. So this is a 30 degree angle here. So next up, I'd like to show you a little applet to just kind of help you visualize reference angles because they can be tricky at first. So let me pull that up for you. Okay, so this will allow you to move a point into any of the 4 quadrants, and it'll tell you the angle measure theta, which is the angle starting from the positive x-axis up to your terminal side, which you're moving. And it will also tell you what alpha is, and alpha is the reference angle in this case. So in quadrant 1, the reference angle is always equal to the actual angle itself. When we get into quadrant 2, however, things change. So the reference angle is now 180 degrees minus whatever theta is, and that leftover is your reference angle. Notice how the program always drops a vertical line from the point P down to the x-axis. That's always how reference angles work. If I move into quadrant 3, the same thing happens. I have, from point P, I have a line created, in this case, up to the x-axis. So it's always that the point in question is always going to the x-axis. This angle measure itself is 234 degrees, so it's just what's left over after 180. So for quadrant 3, actually, let me write these up for you because it would be good for you to know. So for quadrant 1, theta is just equal to alpha. For quadrant 2, your reference angle is going to be 180 minus whatever theta is. Quadrant 3, your reference angle alpha is going to be theta minus 180 degrees. That gives you the leftover after the 180 degrees. When you get into quadrant 4, now that reference angle is 360 degrees. I should put degrees on here to be precise, minus theta. So whatever your angle measure is, subtract that from 360 degrees, and that'll give you the leftover, which is your reference angle. So if you're ever unsure what a reference angle is for any particular angle measure, you can use this app to kind of help you out. It'll let you move the points around. So let's see how reference angles can be helpful, and let's evaluate the 6 trig functions at theta equals 240 degrees using reference angles. Okay, so 240 degrees, that's in quadrant 3. So I'm going to draw this angle measure. Actually, you know what? I'm going to do my axes in black. I'm going to draw an angle measure in quadrant 3. So this is 240 degrees. So what we just learned is the reference angle in quadrant 3 is the angle measure minus 180. So if I do 240 minus 180, that gives me a reference angle of 60 degrees. So this reference angle, which I'll just draw in green, 60 degrees. Okay, great. So we know some things about 60-degree triangles, especially when one angle is a right angle. That means this angle is 30. So I have a 30, 60, 90-degree triangle. The ratio of sides then is 1 square root of 3, 2. So the side opposite the 30-degree angle is 1. The side opposite the 60-degree angle is the square root of 3, and the hypotenuse is 2. Now, I'm in quadrant 3. So what that means is the x value is negative, the y value is negative. Next, what I can do here is basically just answer and say, so starting with sine of 240 degrees, it's going to be the same thing as sine of 60 degrees. So for my reference angle, sine 60 degrees, it's the opposite side, so negative root 3 over the hypotenuse, so over 2. And because I used positive and negative for my x and y, I actually already have this corrected for the sine as well. So the sine of 240 degrees is root 3 over 2. If I wasn't sure that I had that actual sign corrected, just remember, all students take calculus. So this means that the only values that are going to be positive are tangent and cotangent. So sine should be negative. So this is right. Cosine 240 degrees is going to be the same as cosine of 60 degrees in this setup. So it's the adjacent over the hypotenuse. The adjacent is negative 1, the hypotenuse is 2. The tangent of 240 degrees is the opposite side over the adjacent side. So negative root 3 over negative 1, which if you'll notice would be positive root 3. So just like we said, the tangent is positive in this. The tangent is positive in this setup. The tangent is positive in this quadrant. The remaining trig functions are going to be cosecant, so cosecant 240, secant, and cotangent. Cosecant is the inverse of sine. If we flip the sine 2 over square root of 3, we would need to multiply by square root of 3 over itself. And I'm going to move that negative up to make it a little bit nicer looking. So negative 2 root 3 over 3. Secant of 240 is going to be 2 over negative 1, which is negative 2. Cotangent of 240 would be negative 1 over negative root 3, which, if I rationalize the denominator, would be negative, sorry, the negatives are canceling. So it would be positive root 3 divided by 3. So those are the remaining trig functions. Cofunction identities. So if you'll notice, we have a lot of terms in trigonometry that are similar. So we have sine and cosine, tangent and cotangent, secant and cosecant. And there's a very good reason why these are named the way they are. So the reason that they're named that way is this. They're always just 90 degrees off from each other. The cofunctions are always 90 degrees off from each other. Let me show you what I mean. So if I have a right triangle, a 3, 4, 5 triangle, this is a very special triangle where the ratio of sides is all integers. So it's an easy one to do examples with. So if I have an angle measure theta on a triangle that is 3, 4, 5, then the cosine of that angle measure would be the adjacent side over the hypotenuse, which is 4/5. Now, this angle, I don't know what theta is, but I could always know what this angle would be by taking 90 degrees minus that angle measure, so 90 minus theta. Now, if I were to calculate using that as my observed angle, if I did the sine of 90 degrees minus theta, then that would be the opposite of that side. Opposite of that side is 4. The hypotenuse is still 5. So the result here is still 4/5. So if you take an angle measure, subtract it from 90 degrees, the sine and the cosine would agree with those two different angle measures. So they're cofunctions of one another. The co comes from complementary, which means two angles that add up to 90 degrees. So that's why they're named the way they are. This relationship works for secant and cosecant, tangent and cotangent, and if you turn the direction of these things around, it works just as well. Inverse trig functions. Since every angle has a unique value for sine, cosine, and tangent, we can go in reverse, which means we can take the values of sine, cosine, and tangent, which would be a ratio of two sides of a triangle, and look up the angle measure that's associated with each function. And that's through what's called the arc function. So you have arc sine, arc cosine, arc tangent, and they're defined for the secant, cosecant, and cotangent as well. And they're often notated as the trig function raised to the -1 power. So sine to the -1x is the same thing as the arc sine of x. So what you're doing is you're inputting a ratio of sides of a triangle, and the output is an angle measure. So let's see how this might work. So let's find the value of theta in each of the following situations. You may assume theta is in between 0 degrees inclusive, 360 degrees exclusive. So we want to figure out for what values of theta cosine is equal to the square root of 3/2. So in order to solve this, technically what we're doing is doing the inverse cosine. So this basically is saying, theta is equal to the arc cosine, or the inverse cosine, of the square root of 3/2. So you can think of it that way. Or you can kind of think of it a little bit more, less abstract. So if cosine of theta is square root of 3/2, let's draw a right triangle. I need an observed angle. We'll call that theta. And cosine of theta is the square root of 3/2. Cosine is the adjacent side divided by the hypotenuse. Now if two sides are 2 and the square root of 3, the remaining side is going to be 1. You can solve for it using the Pythagorean theorem, or you can just be certain of it because we know about 30, 60, 90 triangles. But what's important is the angle measure that's opposite theta is 1, which means this angle measure is 30 degrees. So that tells me that 30 degrees is one of the angle measures that works. It turns out there's actually two, because I'm going between 0 and 360 degrees. I know that cosine can be positive in quadrant 1, but also in quadrant 4. And if cosine can be positive in quadrant 1 and quadrant 4, then what that means is I can actually have two different answers. But they would have the same reference angle. And that reference angle would be 30 degrees. So I just need to figure out then, what is this angle measure for a reference angle of 30 degrees? Well, the entire rotation has to be 360 degrees. So if I take 360 degrees minus 30 degrees, I get 330. So 330 degrees is another angle measure that would result in the cosine of that angle being square root of 3/2. Let's find an angle measure whose tangent is -√3. So again, I'm just going to start with a right triangle. So I call this my reference angle theta, or my observed angle theta, I should say. Tangent I know to be the opposite side over the adjacent side. Now, you'll notice I put a 1 down here without doing any calculation. And the reason I'm okay with doing that is because I can definitely write any number, no matter what that number is, as a value over 1. That's perfectly fine. So that means this remaining side has to be 2. Now, I'm going to correct for the sign, the positive and negative sign that is, with respect to the all students take calculus. So I'm really not concerned with that side being negative root 3. It's only important to me that it's square root of 3, because opposite the square root of 3 is a reference angle of 60 degrees. But I need tangent to be negative. So tangent is positive in quadrant 1, it's negative in quadrant 2, it's positive in quadrant 3, and it's also negative in quadrant 4. So the angle measures that would work, a 60 degree reference angle in quadrant 2 and a 60 degree reference angle in quadrant 4. So let's see how this works. So a 60 degree reference angle in quadrant 2, I would take the actual angle plus my reference angle would have to add up to 180 degrees. So 180 minus 60 would give me 120 degrees. So one angle measure is 120 degrees. In quadrant 4, I know that the entire rotation of the circle is 360. So that means I would have to go 300 degrees and then 60 more, which is my reference. Or if I could just look at it as 360 minus 60, that's basically what I did. That angle, the actual angle, is 300 degrees. All right, let's look at some use of the calculator here. There are definitely going to be times where you're able to use the calculator in the course, although a lot of times you'll be asked to come up with exact results. If you're asked for exact results, you need answers in terms of square roots and fractions. If you're asked for approximate results, you're welcome to use your calculator. So let's just see how we do it for random angle measure. So let's calculate the sine of 77.41 degrees. So just first make sure you're in degree mode. Get into that habit, because when we start changing between modes, you'll want to check every single time. So the sine of 77.41 degrees, as long as I'm in degree mode, I get the correct answer, 9760. Rounded to 4 decimal places, and the rounding, just follow the instructions in your homework. Secant of 127 degrees, 14 minutes and 22 seconds. Well, we don't have a button for secant, but we do know that secant is the inverse of cosine. So just be careful. That button right there, that's not the inverse of cosine. That is the arc cosine. So as I was showing you earlier with the functions where you take a ratio of sides and get an angle measure back out. So if you want to do secant, you do 1 divided by cosine, and then just type in your angle measure. And since this is in degrees, minutes, and seconds, just remember under the angle menu, you'll find the degrees and the minutes. And then the seconds, you have to do alpha and the plus sign, so 22 seconds. And I get negative 1.6525. All right. Arc cosine of 0.2123. it's definitely a good idea to start getting into the habit of reading this instead of as the inverse of the cosine. Read it as arc cosine, because that'll help you remember as you're doing this more and more that you're not doing 1 divided by cosine, that you're doing this cosine to the -1 power, which means the arc cosine. And just type in your value, and the output here is a degree measure. So 77 point, I'll do 74 degrees. Follow the instructions for rounding in your homework. If it asks for degrees, minutes, seconds, just do second and angle and tell it to convert to degrees, minutes, seconds. And then that will give you that angle measure. Okay. Lastly, the arc cosecant of 1.2531. So this is a little bit tricky, but just recall the relationship here. We know that cosecant of theta and sine theta are related this way. Cosecant is just 1 over sine. When it comes to arc cosecant, let me do of an x here to be proper. It's going to be the arc sine of 1 over the input value. So it's a little bit trickier because the 1 over is on the inside of the parentheses here rather than on the outside, as you would if you were just doing cosecant. So you do arc sine 1 divided by that value that's given, 1.2531, and the output here is 52.94 degrees. Let's do a little bit more solving, but this time with the calculator. Find the value of alpha in 0 to 90 degrees that satisfies the following statements. First, the tangent of alpha equals 0.8971. So basically what that means, to solve this, we say alpha is the arctangent of 0.8971. Okay, so it's kind of like with solving equations. Think about it like this. If I start with tangent alpha equals 0.8971, and I take the arctangent of both sides, arctangent and tangent are inverse functions. And inverse functions mean when you apply one operation and get an output value, put it into the inverse function, you get right back to where you started from. So arctangent and tangent cancel each other out. So that's why I'm using this kind of next step in the operation. Okay, now the calculator is going to find that for us. Luckily, there is a button for arctangent, so second and tan gives you the arctangent, 0.8971, and that gives me an angle measure of 41.9 degrees. Let's try the next one. Secant of alpha is equal to 2.2165. So that means alpha is the arcsecant of 2.2165. Or it's probably a good idea to just write it as arc cosine of 1 over this thing. So if I do arc cosine of 1 divided by 2.2165, I get 63 degrees, 63.2 degrees. One thing, if this seems tricky, one thing to kind of rest assured of. Let's say you tried to do, 1 divided by arc cosine of the original number, 2.2165. The range of cosine is a number between -1 and +1. So any number that's larger than 1 is going to be a bad value. So you're going to get a domain error, which means it's basically telling you that your input is incorrect. So in order to do an arcsecant, you have to do 1 over the given value, and then do the arc cosine. So that's everything for this lesson. Good luck with the homework, and see you in the next lesson.